Hello and welcome back to another YouTube video. Today we're going over our third quiz inside of Khan Academy with our limit and continuity unit. We're going to be solving a little bit more difficult limit expressions than last time. We might have to do some eliminating discontinuities in this process. Don't worry, I'll be walking us through all of these. Make sure to like and subscribe if you haven't already. The next 2 days is going to be going over SAT content, so definitely be excited for that. But for now, let's get to our first question in this quiz. So we want to find the limit of x over sine of x as x approaches 0. Direct substitution and other algebraic methods that we did in the last video, they don't work with this one. We can just look at the graph and then estimate this limit. We can see as x approaches 0, we can use something called the squeeze theorem by using two functions. How the squeeze theorem usually works. This might not be the case here. We want to essentially squeeze this function f of x between both a above function and a below function that are both defined at x approaches 0. And this way we will actually get a if you squeeze the function between an above and below function that are both defined, and this is in between those, then we can estimate the limit for the value as x approaches 0. So we can pick two functions that go above and below. In this case, this does not match the typical squeeze theorem. Typical squeeze theorem, just want to show us we will have something that goes above. Maybe instead of x over sine of x, we have x squared plus 1. This function is always above, etc. It will look like this. Then you would pick something that's always below, maybe negative x squared plus 1. Within this range, and then you can see both of these are defined as x approaches 0 as positive 1, and since our function f of x is squeezed between these two values, we can then approximate the limit to be equal to 1 as well. Now notice both the above and below function, the above function has to be above f of x at all values, the below function has to be below f of x at all values in order to squeeze them into a certain area. And as we can see here, h of x, it is above the function to the left of 0 and then below the function. So it's not going to work as an above function. And the same thing with g of x. It's below and then it's above. These are not applicable because we can see here. Yep, we need one function to be always below f of x and the output of the other function to be always above. That is not the case with this example. Okay. Now we're going to be looking at some trigonometric limits here. How we can define this is, first of all, direct substitution. It's not going to work. If you know how these questions solve, the sine of pi over 2 is equal to positive 1. 1 minus 1 is 0. So in this case, it's not going to work to say to do direct substitution as our denominator is undefined. Instead, how we can solve something like this is that we are first going to use trigonometric identities, and then we're going to use difference of squares. So the identities that we're going to use in order to solve this problem, first we're going to have to rewrite cotangent squared of x. Our first step is to rewrite this in terms of sine and cosine. So as we should know, cotangent is equal to the adjacent over the opposite, or cosine over sine. So we can rewrite cosine squared of x as cotangent squared of x as cosine squared of x divided by sine squared of x. And so now our expression is going to look like this. Our numerator is cosine squared of x divided by sine squared of x. And our denominator is 1 minus sine of x. Like this. We're going to go ahead and combine both denominators. When we have two denominators, we can move them next to each other and just multiply the two denominators together. So we're going to rewrite this expression as cosine squared of x in our numerator, and then our denominator is just these two multiplied by each other. So now we have sine squared of x times 1 minus sine of x in parentheses. Now we're going to use Pythagorean identities to rewrite cosine squared of x. So we should know cosine squared of x plus sine squared of x is equal to 1 via a Pythagorean identity. So in order to solve this for cosine, we subtract 1 from each side. So cosine squared of x is actually equal to sine squared of x minus 1. So we're going to replace the numerator with sine squared of x minus 1. Now, I highly recommend, if you are confused with how these identities work, to research Pythagorean identities, research double angle identities, research just these trigonometrics in general, because these are all talked about in pre-calculus and are considered a precursor. So you, in calculus, you're pretty much expected to know how all of these work. They're really in-depth in solving these limit expressions, but you don't see them too much when we're dealing with differentials, as you'll see in the later units as we go over them. But now our numerator is sine squared of x minus 1, and we're going to use difference of squares. This is an algebra 1 formula. If we have two terms that are squares, and they are subtracting difference of squares, we can order them like this. We can square root both the terms and separate into factors, one that is positive and one that is negative. Oh yeah, so real quick, it's not sine squared x, it's 1 minus sine squared, like this, because remember, if we have the identity, we're going to subtract sine squared. Let me rewrite this out. So remember, we had cosine squared of x in our numerator, and this is part of the Pythagorean identity. Cosine squared of x plus sine squared of x is equal to positive 1, and in order to get cosine squared of x by itself, that's what we had in our numerator, we just subtract sine squared of x from both sides, so it cancels out on our left side, and we're left with 1 minus sine squared of x on our right side, and that way we can now substitute cosine squared of x with 1 minus sine squared of x. Alright, so that's why our numerator is 1 minus sine squared of x, and now we're going to use a difference of squares. The square root of 1 is 1, the square root of sine squared of x is just sine of x, so we're going to separate 1 minus sine squared of x into the two factors, 1 minus sine of x, and then 1 plus sine of x. This is how difference of squares works, if you search up the formula for that. So we can officially replace 1 minus sine squared of x with these two factors, and now we should notice that we have a 1 minus sine of x on our numerator and a 1 minus sine of x on our denominator, and that's the whole point, because that 1 minus sine of x in our denominator is what made this whole expression undefined when we substituted in x approaches the pi over 2. And remember, if we're solving this in an FRQ, we need to have this limit expression with each step of our equation. I'm not going to write it out with each of these here, but I would have to, for example, when I separated cotangent squared of x into cosine squared of x over sine squared of x, you'd have to write it like this. The limit as x approaches pi over 2 is, well, of whatever this is. And then until you direct substitute, you're going to keep this limit expression with each step of our simplification. Okay, now we're at this step. We can cancel out 1 minus sine of x on both the numerator and denominator. Now we're left with 1 plus sine of x in our numerator and then sine squared of x in our denominator. And from here, we can direct substitute, meaning in the FRQ, we wouldn't have to put this limit expression anymore. Substituting into this, let me rewrite. 1 plus sine of x over sine squared of x. Remember, the sine of pi over 2 is equal to 1, so our denominator is just 1 squared, which is equal to 1, and our numerator is 1 plus 1. 1 plus 1 is 2. We're left with 2 divided by 1, which is equal to 2, so our limit expression is equal to 2. Alright, so knowing these identities are extremely important for these types of questions. If you have any questions about this specific specific question in the comments, be sure to let me know, because this stuff is quite difficult. Highly recommend. I'll provide some sources related to pre-calculus, manipulating trigonometric equations and using all these different identities. Okay, moving on to more easier stuff. This is just polynomials. Notice we cannot direct substitute here because we just left with 1 minus 1, which gets 0 in our denominator. We obviously don't want that to be the case. What we're going to do here is that we are going to take the greatest common factor of both the numerator and denominator, and then we're going to cancel something out. So notice we can take the greatest common factor of our denominator as 12x squared. So we're going to factor out 12x squared from each of the terms. We are just left with simply x plus 1. Then our denominator, we're going to factor out x squared from each of the terms. And we are simply left with x squared minus 1. Now from here, we can cancel out these two to make it a more simple equation, but we still need to eliminate the discontinuity. Notice we also have difference of squares, just like our last question. X squared minus 1, we can separate this into the two factors, x plus 1 and x minus 1. If you're confused how this works, if you wanted to, you could FOIL or expand these two parentheses back out, and you would get our x squared minus 1. But now we have 12 parentheses x plus 1, and then we have x plus 1 over x minus 1. In our denominator, we can cancel out our x plus 1 factor. Now we are left with simply 12 over x minus 1. Now we can direct substitute. Now, remember, we still have to include this limit expression with all previous steps up until this point. But now, since we substitute, we don't need it anymore. This is equal to 12 over negative 1 minus 1. Negative 1 minus 1 is equal to negative 2. 12 divided by negative 2 is negative 6. So B is the correct answer with this question. All right. Moving on to this next, we have a limit expression dealing with roots. Square roots. In this case, we use the conjugate method. So we're going to take the conjugate of this denominator expression down here, because once again, if you solved this out, if you direct substituted, you would get 0 in the denominator, and we cannot solve like normal when that is the case. We need to eliminate the discontinuity. How we do this, we multiply by the conjugate. The conjugate is just the positive version. So instead of minus 4, it's the exact same thing, but now it's plus 4. And what we do to the numerator, we have to do to the denominator. So we're going to multiply our whole expression by 4x, well, the square root of 4x plus 4, plus 4 this time. This is the conjugate of our denominator. Going to do the exact same thing that we did to our numerator to our denominator. So we're also going to multiply that by the square root of 4x plus 4 plus 4. And from here, we know that our numerator is just going to multiply with each other. It'll look like that in parentheses. We'll keep it like that so far. But our denominator, the square roots are going to multiply, and those are going to cancel out. So we are left, and notice this is difference of squares, so we don't have to worry about foiling the outside and the inner terms as they just cancel out. That's why we do these conjugates. They're pretty easy to solve. So when we multiply square root of 4x plus 4 times the square root of 4x plus 4, we are simply left with 4x plus 4. The square roots cancel out. And then we multiply negative 4 times positive 4, and we get negative 16. 4 minus negative 16 is negative 12. So now we have 4x minus 12. That is in our denominator. And now our numerator, we have x minus 3. We're not going to multiply this out because I'll show you in the next step. We're going to simplify our denominator by taking out the greatest common factor. All right, times our conjugate. Now next step is just going to be take the greatest common factor out of our denominator. And if you don't notice already, we can divide both the terms in our denominator by 4. When we do that, our 4x minus 12 turns into 4 parentheses x minus 3. And from here, we have these two factors. We're just going to cancel them out. This canceling out eliminates the discontinuity. Remember, we're still going to have this limit of x approaches 3 for each of these steps of the equation, or else you're going to get points off in the FRQ. Now our expression is simply the limit. I'll do the limit expression for this one, but just know every single step you have to include this. The limit as x approaches 3 of the square root of 4x plus 4 over 4. We can substitute in x equals 3 at this point. Now 4 times 3 is 12. 12 plus 4 is 16. Square root of 16 is 4. We have 4 plus 4 is 8. Divided by 4 is 2. So our limit as x approaches 3 of x minus 3 over the square root of 4x plus 4 minus 4 is equal to positive 2. All right, last step here. Very simple. How we use these flowcharts, we first start with direct substitution as it says. So let's try direct substitution. We substitute in 3. With these, you have to do both numerator and denominator, because then we're going to determine if we get indeterminate form or an asymptote. Asymptote is when we have a value for the numerator but a 0 for the denominator, which means we can't really do anything from there. But let's go ahead and check. When we substitute into the denominator, we get 3 minus 3 is equal to 0. So now we're going to substitute into the numerator. We get 9 minus 27, negative 18, plus 18 is 0. So we get our indeterminate form. So first we do direct substitution, and then we get indeterminate form. Now notice we get three pathways from indeterminate form. We have trig identities, which was our second question. We get conjugates, which was our fourth question. And we have factoring, which was our third question, and is what we're going to do here. If you have a quadratic, probably factoring is the right answer. When we factor this quadratic, remember how we do these. What two numbers multiply to 18 and add to -9? Those two numbers are 3 and 6. More specifically, -3 and -6. Notice when you combine them, they equal -9. When they multiply, they equal +18. So we can simplify our quadratic in the numerator into x minus 3, parentheses, x minus 6. If you have any trouble with this factoring, I highly recommend you visiting Algebra 1. Inside of Khan Academy, and they have a factoring section which will help you out. Now we have this canceling out process, and now we can direct substitute once again for x equals 3 into our numerator, and we get 9 minus 6, which is equal, no, we get 3 minus 6, my apologies, which is equal to -3. So the limit of g of x as x approaches 3 is -3. So our first step is that we direct substituted. We found indeterminate form, and then we factored, and then we direct substituted again, and then we found the limit. Notice we have to include each of these. You won't see this type of question on the AP exam, but it's good to know as a process. Yep, direct substitution, x3, we got 0 on the numerator, 0 on the denominator, that's indeterminate form. We factored the quadratic, canceled out that factor. Now we could direct substitute and not result in indeterminate form. We found the limit of -3. Okay, this is definitely the essence of limits and continuity on this exam. You're going to see a lot of these questions, a lot of these type of questions. As you notice, they're more difficult, they're more of a calculus level. Now, if you have any questions, especially with those trig identities or with anything other, like the conjugates, difference of squares, factoring, and the such, let me know in the comments. Make sure to subscribe if you haven't already, and I'll see you guys for SAT practice over the next upcoming days. Goodbye.